Welcome back to the lectures on perovskite PV technology. In this video we will discuss the different device structures of halide perovskite solar cells. The conventional device structure of a perovskite solar cell is based on the planar configuration as shown here. Next to the device structure, I show the energy diagram to explain the operating principle of perovskite solar cells. The perovskite absorber layer is sandwiched between a hole transport layer and an electron transport layer. The conduction band of the electron transport layer is lower than that of the perovskite, so light-excited electrons are separated from the holes by the injection into the electron transport layer. Vice versa, the valence band of the hole transport layer at the back of the solar cell is higher than for the perovskite, and therefore the holes are injected in the hole transport layer. Common electron transport layers include, for instance, titanium oxide, zinc oxide, tin oxide, and PCBM. And common hole transport layers include spiromeotat, PTAA, P.PSS, and, for instance, nickel oxide. In the planar structure, two types of solar cell structures exist, namely the NIP and PIN. Notice that this is quite similar to the NIP and PIN structures discussed for thin film silicon solar cells. NIP and PIN describe the sequence and order of the deposition of the various layers to form the solar cell structure. The NIP structure is referred to as the regular structure, as it evolved from the conventional mesoporous structure not discussed here that was used for the first generation of perovskite solar cells. In the NIP structure, the electron transport layer is first deposited on the glass TCO strip. After deposition of the perovskite, the whole transport layer is deposited before the metallic back contact is deposited. In a NIP configuration, the light is incident from the side of the electron transport layer. The PIN structure is also referred to as the inverted structure. In the PIN structure, the whole transport layer is first deposited on the glass TCO substrate before the perovskite is deposited. The electron transport layer is deposited before the metallic back contact is deposited. So in a PIN cell, the light is incident on the junction from the side of the whole transport layer. Note that the record efficiencies of the halide perovskite PV technologies have been increased rapidly on lab scale the last decades. Nevertheless, the perovskite PV technology is facing still some crucial challenges before it can be commercialized. Therefore, the research is still focused on some fundamental questions. The PV technology is still in the phase of a medium technical readiness level. Here I will discuss shortly a few important challenges that have been tackled or still need to be tackled. The first challenge is that the performance of the solar cell depends on the operation history of the solar cell. This effect is called hysteresis. Let's look at a typical JV measurement of a perovskite solar cell. Here the current density is measured by scanning the voltage in forward bias direction. It leads to a very nice and sharp JV curve. However, if the next JV curve is measured by scanning the voltage in the reverse direction, the JV curve does not look the same in reference to the opposite scanning direction. This hysteresis effect shows that charge carrier collection has been changed. Several studies have shown that this effect is caused by movement of charge in the solar cell in electric fields that are applied in the cell, like during the JV measurements shown here. The most likely candidate are anions and cations that form the perovskites. When a strong external field is applied, they might become mobile and move through the layer and accumulate at interfaces. This can be at the interface between the perovskite with either the electron or the hole transport layer. The hysteresis effect can depend on the device configuration and on the materials used for the electron and hole transport layers. Many solutions to this hysteresis problems have been published in the last year. The solutions are focused on the inclusion of passivation layers or treatments of the interfaces between the perovskite material and the electron and hole transport layers. Adding a monolayer of a suitable buffer element like fullerene or the monolayer of chlorine can improve the binding at the interface and the structural and lattice matching between the materials. These type of solutions prevent the charge accumulation at the interfaces and enhances the electron transfer into the electron transport layer and the hole transfer into the hole transfer layer and reduce the hysteresis. Another very important challenge is that perovskite solar cells suffer from degradation of the performance in time. This graph shows a normalized performance of a normal perovskite solar cell in ambient air in time. The efficiency almost drops to 0% in 40 hours. This effect cannot be reversed with a thermal layer, so the effect is different from, for instance, the Stable-Wronski effect in amorphous silicon we discussed earlier, which is referred to as a metastable effect, and it can be recovered under a thermal anneal. If the same experiment is repeated in dry air or in a nitrogen atmosphere, the degradation is delayed. This demonstrates that humidity plays an important role and suggests that the effect is a chemical instability. The perovskite materials can be decomposed when exposed to humidity. The presence of water can accelerate the chemical degradation of the perovskite phase under illumination and heat. The structure of the lattice can be significantly modified. The lead atom and the two iodine atoms form a molecule that becomes an interstitial entity in the lattice, deteriorating the electro-optical properties of the material. Here you see examples of the paper of Habesoitinger on how the color and transparency of the samples can change over time. In addition, some electrode materials such as aluminium, silver could react with the perovskite in a moisture environment as well. Finally, some halide perovskite materials can spontaneously decompose under relatively moderate temperatures as well. Several approaches have been explored to prevent the degradation of perovskite solar cells. A promising approach is to modify the nature of the lattice itself to make the material more resistant against the presence of water. It has been demonstrated that halide perovskite materials with a mixture of various cations and halide anions can significantly delay or remove the chemical degradation. The X-cation can be a mixture of organic and inorganic materials like cesium, rubidium, methylammonium, and formamidinium. The halide anion can be a mixture of iodine and bromine. Improved stability and efficiencies have been demonstrated in which the efficiency only shows a relative degradation of a few percent in 1,000 up to 8,000 hours. The last years, the first tandem and triple junction solar cells based on only perovskite absorbers have been successfully demonstrated as well. The conversion efficiencies of tandem cells exceed those of the single junction perovskite solar cells as expected. The updated info on the record of the best conversion efficiencies for perovskite solar cells and the other PV technologies I will discuss at the end of the part 2 of this solar energy MOOC. Another interesting application of halide perovskites is that they are being explored as a potential top cell junction in combination with the conventional crystalline silicon bottom cell in a high efficiency tandem cell. We will discuss the hybrid structures at the end of part 2 of this solar energy MOOC as well. A final note is that up to date, no reliable PV module product based on perovskite material is on the market yet, nor a reliable PV module has been demonstrated in the outdoors. So commercial perovskite PV modules is still work in progress. In summary, for photovoltaics, organic, inorganic perovskites are used as well. In these perovskites, the large cation A is organic and often methyl ammonium is used. X is a halogen such as iodine, chlorine or bromine, often in a mixed halide material. The cation B usually contains lead, while tin can also be used. The direct band gap and the electrical properties of halide perovskites make it an ideal material for thin film PV technologies. We have discussed the various device structures like a mesoporous regular and the inverted planar configuration. The challenges of the PV technology and potential solution for the perovskite PV technologies have been discussed, like the hysteresis effect and the degradation of the performance due to humidity. Now we have introduced all PV technologies in the second part of this MOOC. We are going to compare all different PV technologies using the metrics we have introduced earlier. So see you in the next video lecture.